Hello everyone, welcome to my presentation. I'm Sachin Ashok, a second-year graduate student at University of Illinois at Urbana-Champaign. Today I'll be presenting iBox, which is a data-driven network path simulator. This is joint work with my colleagues at Microsoft Research India, Shubham, Nagarajan, Venkat, and Sundarajan. The motivation for our problem is rooted in the observation that most networked applications need to be tested in real-world conditions in order to achieve good performance. For example, real-time interactive streaming apps like Teams or Zoom, on-demand streaming like Netflix, or for tuning parameters for congestion control or video codecs. At the same time, network parameters like Planet Lab or Pantheon often lack the scale and reach to be representative of real-world networks. So usually, flighting new features to real users in a production setting is the norm. But this tends to be quite expensive as well as potentially disruptive, as new features can introduce performance regressions. Flighting is also particularly time-consuming if you need to use ML-based training, which usually requires thousands of iterations to converge, as each iteration would take a long time in a production setting. So then, is network simulation the answer to our problem? So let's take a look at what's possible with network simulation. There are three broad kinds. The first is event-driven simulation, where we string together a network of simulated components like buffers and links, like in NS3 or NetM. This obviously provides a realistic behavior at a component level, but it isn't quite informed by data, as we don't know how to set realistic parameters for our simulation. Now, the second kind is trace-driven replay, where real-world traces are collected and replayed during simulation. For example, like in CellSim or Mahi Mahi. Although these simulations are obviously informed by data, they're not realistic as they do not account for the impact caused by a new, different sender under test. Finally, there is some recent work on calibrating simulators, for example, like in Pantheon, which tries to learn values for network parameters, but it does not model crucial network phenomena like cross-traffic. So the question is, can we do better? This is where iBox comes in. iBox stands for Internet in a Box. We take the speed and convenience of a simulator and combine it with the realism of real-world networks to get iBox. At the heart of it, iBox is a network path simulator which learns from real-world data and recreates realistic end-to-end network behavior of a target network. At a very high level, this is how it works. Let's say you have a network path through the internet between a sender S and a receiver R. We collect traces from this path in the form of input-output packet traces. The input corresponds to packet sent timestamps and the packet sizes, and the output corresponds to the received timestamps and the corresponding delay that each packet faced. These traces are then used for network model training, and this is the training phase. We generate one model per network path, and these network models are aggregated within the iBox model repository. Now, to run simulations, we sample an iBox network model from the repository and configure the simulator. And to test a new protocol on this learned path from S to R, we pass the packets from the sender via the iBox simulator, delay or drop packets within the simulator, and pass the output to the receiver. This is our testing phase. And just to be clear, S and R here are real applications that are provided by the users of iBox. iBox only provides a substitute for the real internet. One of the most promising use cases for this work is to help in A/B testing of a product. Imagine the scenario where you have a production system serving many clients. In A/B testing, when developers implement a new feature, they roll it out to a small percentage of clients, like version B as shown here. Once it is operational, they collect traces corresponding to version B from both the client as well as the service. They then process these logs, compare the performance of A and B, and fine-tune B based off their observations. In cases where B works well, they might roll it out to all the users. But there are many problems with this approach. The first is that it's quite slow because iterations take too long in production. Second, it is risky as version B could contain bugs which would result in bad service. And finally, it is expensive since the bad service and performance regressions can cause customers to drop their product altogether. Now, instead, if a realistic simulator like iBox was available, it could replace the real internet with a simulator, and when developers implement a new feature, they test it by running it against the iBox simulator, which simulated test clients are connected to. And just like before, they can collect logs from both the simulated client as well as the service. Now, like in the previous scenario, they process these logs, compare A and B, and fine-tune B. This would enable the feature development cycle to be fast since we are using simulations, safe from regressions as iBox is able to detect regressions before they go to production, as well as cheap as customers are not exposed to defective features. So let's dive a little more deeper into how iBox is designed. First, we use a simplified model to capture key characteristics of the network path between the sender and receiver. So let's imagine a sender and receiver communicating through a wide area network path. We model this path as a single bottleneck consisting of a link with a buffer of size b, a bottleneck supporting a bandwidth of small b, and the path itself imposing a propagation delay of duration d. These three parameters b, small b, and d are the static parameters of the initial simplified model. At a high level, the static parameters are estimated as follows. The bottleneck bandwidth b is based off the peak receiving rate seen in the trace. The propagation delay d is based on the minimum delay experienced by packets in the trace. And the buffer size b is based on the bottleneck bandwidth and the difference between the min and the max delay faced by packets in the trace, which roughly corresponds to the maximum queuing delay a packet can face. There's also a distinction to keep in mind when you compare online and offline estimation. In online estimation, estimates improve over time as more observations are made. For example, in the case of congestion controller estimating available bandwidth. Whereas in our scenario, which is the offline case, the entire trace is available offline, so our estimates can benefit from the entire set of observations. Additionally, we can also combine information from multiple flows on the same day to get better estimates. For example, in this plot, the estimated buffer size is shown on the y-axis, and dates corresponding to the traces are shown on the x-axis. We can combine information from multiple traces from the same day to get a better estimate for buffer size. Now let's look at the dynamic parameters that iBox estimates. The model from before is too simplified as it does not account for cross-traffic. So next, we model cross-traffic via a single parameter called C. In our first iteration of estimating cross-traffic, we estimate it as a static rate time series, which we call non-reactive cross-traffic or NRCT. So let's see how we can estimate it. Let me just clear up this diagram. Our estimation in a nutshell benefits from the observation that a buffer is governed by three phenomena: packets entering the buffer due to our self-traffic, packets entering the buffer due to cross-traffic, and then packets draining from the buffer at the allocated bandwidth. First, we take two observations of the delay faced by the kth and the k minus nth packet, which corresponds to q of k and q of k minus n. As I said before, the difference between these two quantities should be explained by three factors: the cross-traffic packets entering the buffer, which is c, our packets draining from the buffer, which is the sum over si, and finally packets leaving the buffer due to the link draining, which is denoted as drain time into b. Now, since we know how many packets we have put in and we have earlier estimated the rate at which the queue drains, we can simply rearrange the terms in this equation to calculate the amount of bytes cross-traffic must have sent into this buffer in this duration. We then divide by the time gap between our observations to get an estimate of the rate of cross-traffic. Now this estimate shown here is just a single value. For an entire trace, we would have many such pairs of packets on which we run this estimate in a sliding window manner, which gives us a time series of the rate of cross-traffic. So how well does this work? Here's an example from simulation. What you see here is the ground truth of the cross-traffic that was recorded. On the x-axis you have time and on the y-axis you have rate. We run the process mentioned before and the blue curve is the estimate that we get. We can see that the estimate very closely matches the ground truth and therefore can be used to replay realistic cross-traffic patterns in simulation. But is non-reactive cross-traffic, which is basically just a replay of cross-traffic packets, good enough? Let's see an example experiment which highlights a problem. Imagine a scenario A where you have our sender, which uses TCP cubic, which is an aggressive congestion control protocol. The cross-traffic it competes with is also TCP cubic and hence similarly aggressive. This is what the ground truth cross-traffic measured in scenario A looked like. Now, when we apply our NRCT estimation formula, we get the following estimate for cross-traffic. Note that the match is almost perfect. Now in scenario B, we change our sender protocol from cubic to something more timid like lead-bat, which gives a bandwidth if there is any competition on the link. We keep the cross-traffic the same and similarly aggressive as in scenario A. The ground truth of cross-traffic when lead-bat is used as the self-flow is shown by the red curve. As you can see, the cross-traffic ramps up and gets more share of the bottleneck bandwidth. And quite clearly, there's a big disparity between our previous estimate and the cross-traffic ground truth in this scenario. This is because in the second case, the cross-traffic reacted to the fact that our flow was more timid and was able to ramp up. What this means is that cross-traffic can react differently to different kinds of competing traffic, which static replay cannot capture. So in order to make our cross-traffic reactive, we model cross-traffic as a set of real reactive TCP flows, which we call reactive cross-traffic or RCT. So for example, let's say you have this aggregate volume of overall cross-traffic. What we try to do is to break it down into its individual constituent flows. So instead of a static time series, it would look something like this, where we have our model basically trying to learn how many cross-traffic flows there are, what the nature of these flows are. For example, are they running cubic or Vegas, and also when these flows start and stop. Here in this example, the cross-traffic consists of two flows, one running cubic, which starts at 3 seconds and ends at 10 seconds, and the other runs Vegas, which starts at 5 seconds and ends at 15 seconds. Finally, instead of using any sophisticated formulation here, we use a Bayesian optimization-based search to search for these parameters. I will briefly talk about this search process next. So the algorithm for computing RCT is as follows. We take a raw trace file and parse it. We use the process trace file to estimate basic network parameters like bottleneck bandwidth, propagation delay, and buffer size. We then estimate cross-traffic through the NRCT model. And then we use the NRCT model as a seed point for initializing the RCT model computation. What I mean by that is that when we analyze the NRCT estimate using a change point detection algorithm to find points where massive changes occurred, to find good starting points to seed our search for RCT parameters. For each iteration of RCT model computation, we use a Bayesian approach to select the next set of cross-traffic parameters. In the first iteration, it would be just the seed values. We then use these cross-traffic parameters along with the basic parameters to run a simulation. Now, once we have the trace from simulation, we compute the disparity with respect to the ground truth. If the disparity is too high, then we continue the iteration. If the disparity is low enough, we exit and output the RCT parameters. The search process essentially keeps running until we find good RCT parameters. Here's an example of an RCT configuration obtained via this approach. The configuration specifies 3 flows, all cubic, which start and stop at different times. Now finally, putting all this together, it should be clear that the iBox model we introduced in the beginning is basically a simulator parameterized by network parameters like bottleneck bandwidth, buffer size, propagation delay, and crucially the reactive cross-traffic. Now that I've introduced iBox and talked extensively about its design, I shall be handing over to my collaborator Shubham to talk more about the implementation and the overall evaluation of iBox.
Hello everyone, I am Shubham. I'm a research fellow at Microsoft Research India. I will be talking about evaluation of iBox. Given static parameters in cross-traffic, how do we test a given sender or protocol? We set up a simple dumbbell topology and set the static parameters on the bottleneck link. We send cross-traffic from node CS to CR across the bottleneck link. The sender under test is deployed at node S and the corresponding receiver is deployed at node R. We implement this topology using a popular simulation or emulation platform like NS2, NS3, or NetM. In our paper, we evaluate the accuracy of static parameters, the NRCT and the RCT models. Putting static parameters and cross-traffic model together, we present an overall evaluation of how well iBox is able to predict the performance of network protocols on real-world network paths. In this talk, my focus will be on NRCT and overall evaluation. The evaluation data set consists of real-world traces from a diverse set of geographical locations like India, China, Nepal, and so on. The traces were collected over a period of 1 to 2 years and correspond to a variety of protocols like Cubic, Vegas, and BBR. Also, the traces were collected over various link types like Ethernet, cellular, and Wi-Fi. Coming to non-reactive cross-traffic, we evaluate NRCT in a controlled setting as well as in a real-world setting. In a controlled setting, we evaluate NRCT on traces generated using an emulator. In the real-world setting, we evaluate NRCT on traces collected on real-world networks. In the controlled setting, we generate traces by randomly sampling a set of TCP flows and playing them on a simulator alongside an observation flow. The plot shows the CDF over 200 runs of the normalized error between the NRCT estimate and the ground truth. The 90th percentile error is 11%, which shows that the NRCT model closely matches the ground truth. In traces coming from real-world networks, the ground truth cross-traffic is not observed, making it tough to evaluate NRCT in a real-world setting. However, one idea is to run concurrent connections in a real-world setting. We use 2 evaluation metrics, the underestimation error and the additional cross-traffic estimated. Let us take an example to understand these metrics. We choose a trace with 3 concurrent flows and pick flow 1 as the observed flow and flows 2 and 3 as the cross-traffic flows. The yellow curve in the plot shows the known cross-traffic. The blue curve shows the non-reactive cross-traffic estimated using the observed flow 1. The additional cross traffic estimated is the volume of cross traffic estimate exceeding the known lower bound, which is shown as the blue dotted line area in the plot. The region where the NRCT estimate violates the known lower bound is marked by the red dotted line. Such regions represent the underestimation error. The plot on the right shows the CDF of underestimation error. The underestimation error is quite small, that is under 2% in over 90% of the cases. The additional cross traffic is under 250% in 90% of the cases. For overall evaluation of iBox, we put together the static parameters and the cross traffic model to see how well iBox can test network protocols. We train iBox model on protocol A and test it on an unseen protocol B. In current example, we trained iBox on cubic traces from China's cellular dataset and tested them on BBR traces from the same dataset. The orange dots in the throughput versus delay plot indicate the ground truth, where each dot corresponds to a single TCP transfer. The green dots represent the iBox inference for BBR. As we progress from no cross traffic to a non-reactive cross traffic and then to a reactive cross traffic model, we progressively get better match with respect to ground truth. There are several challenges and future opportunities in this space. The current iBox model is simple and it does not generalize to unmodeled behaviors, such as ISP policing, variable bandwidth, bursty loss, and so on. The current model is trained on TCP cubic, which is an aggressive protocol and explores the network limits. What can be estimated from other protocols is an interesting question to explore. The selective active probing and Bayesian optimization to get better estimates of network parameters is also an interesting research direction. To conclude, iBox is a data-driven network path simulator that learns from the real-world data and faithfully replicates real-world performance of protocols in simulation. Using data to create realism is a promising research direction with a lot of open challenges. The iBox models are available for public download. Please visit aka.ms/ibox for details. Thank you.